Okay, let us go to the other part of this lecture. So, and now the title of this chapter is Limit for Functions through Sequences. Okay, this is a very important and quite difficult topics. So let me immediately give you the theorem and then we will discuss. The aim of this theorem is to reduce, at least at a conceptual level, the notion of limit of function to the notion of limit for sequence. So the theorem is the following. So let me call it LTS, limit through sequences. And so this is the message I want to repeat again. I'm not talking here of limit of sequences, but it is a theorem of limit of functions by using sequences. So, and this is the statement of the theorem. Consider a subset of R, let us call it E, and then X bar, which is an accumulation point, that can also be plus or minus infinity according to what we said yesterday. And then we have a function f from E to R, okay, as usual. Now, we suppose that the limit for x going to x bar of f is equal to some L, again in R bar. That means that it can also be plus infinity or minus infinity. And this is true if and only if for every sequence xn that is contained with its value in the set E minus x bar and tending to x bar as n goes to plus infinity, we have that f of x on n goes to L. Okay? So first, let me reread this theorem because it is quite complicated too. This is the usual stuff. So we have a subset of R that will play the role of the domain of a function f. Then we have an accumulation point of this domain, and then we consider the case in which the limit exists. So we have the limit for x going to x bar of f of x is equal to L. Both x bar and L can be plus or minus infinity. They belong to L bar. Okay, so this is just the idea of regularity. The limit exists. This is true if and only if, which means this is completely equivalent to say that for any arbitrary sequence that lies in the domain but does not touch x bar, however it converges to x bar, so we have a sequence running into the domain. When we apply f to the sequence, then we go to L. This is another sequence. So this is the sequence of the elements of the domain, xn, and this is the sequence of the images. If the elements of the domain tend to x bar, the basis point of the limit, then the images tend to the limit. Okay? I repeat it here, I don't know, 5, 7 times, and so I hope it is well understood. If not, let me try with a picture. So, This is the picture. Each time I say this is a picture, do you know this wonderful song by Peter Gabriel and Laurie Anderson? This is the picture. I always, when I say that, I always, my mind goes to this old and very, very nice song, electronic song. Okay, so this is function. Here we have our basis point x bar. I don't want to play with strange thing discontinuity. Let me be extremely standard here. Here we have L. Sorry. L. So the philosophy of the theorem is the following, is that the limit is L. Remember that this means that whatever neighborhood of L I take, call it V, there exists a neighborhood of x bar. Let me call it U, so this is U and this is V. This U looks like a V, so let me do it again. As usual, it is a mess. Let me restore the x-axis. Doesn't not play any role, but however it is nice. Okay, this is the x-axis. Okay, so this is the idea of limit. Take a V, neighborhood of the limit, and then discover that there exists a neighborhood of the basis point x bar that is mapped through f into V. Okay, now our theorem says that this conclusion is completely equivalent to the following. Consider a sequence going to x bar, remaining in the domain of f, and the sequence is going to x bar, is converging in this case to x bar, without touching the value x bar. Why? Because it is not in the definition of the limit. Remember, in the limit for x going to x bar, the actual behavior in x bar is irrelevant. So this sequence goes to x bar, and let us consider the sequence of the images. It is very simple to consider the sequence of the images. Just look at the images here. Okay, if you want to do it in a complete way, and just project this point on the y-axis, but this is not important. So it happens that as the black points of the sequence on the x-axis approaches x bar, the sequence of the images approaches L. Okay? This is the idea. The strong point is that these two notions are completely equivalent. So from one side, and also from the picture, it is natural that if the limit is L, then when taking a sequence going to x bar, then the images of the sequence will go to L too. This is quite natural. The reverse is less natural. The reverse says that sequences can also cover the whole of the function. And this is, in my opinion, it is not so intuitive, but perhaps for you it is. The point is that the strength of the theorem is here for every sequence. So in order for the sequence to determine the limit of the function, it is essential that this miracle happens for every sequence. This is the main point. Okay? And this is the picture you should keep in mind. And then let us go to the proof. The proof has a simple part and a difficult part. We start with the simple part. Has two parts because it is an equivalence, if and only if. So we have to prove both directions. Prove. So first, we assume, so this is the direct implication, okay? So we assume that the limit for x going to x bar of f of x is equal to L. Okay? Okay, here in principle we should distinguish several cases according to the fact that x bar and L are finite or not. So let us start with the first case. I could do it with neighborhood, but I want to be gradual, okay? This is simpler. So we have both x bar and L finite, and we say let xn with values in the domain of the function e, but never equal to x bar, be an arbitrary sequence that has a limit, and the limit is x bar. Okay? So here there is a point I leave to you. Who guarantees that such a sequence exists? Okay? So why does such a sequence exist? This is a very important question. Okay, when in a proof, when in mathematics I say, I take an object like that, I should always be sure that it exists, and I should also be able to convince the others that it exists. So why does it exist? And the exercise I suggest you is the following. Try to prove the following lemma. There exists a sequence of the type you are interested in, xn, which is as value in e minus x bar, but converges, tends to x bar, if and only if, I write if with 2f, x bar is an accumulation point. Try to prove it, okay? This is an important lemma that probably gives you another insight on what accumulation points are. So, and now a starting point, this sequence exists. Okay? And now what we aim at proving is very simply that the sequence of the images goes to L. Remember, when we want to prove a certain limit, we start with let epsilon larger than 0. Arbitrarily chosen, as usual. So, since this is our assumption for this part of this theorem, the limit for x going to x bar of f of x is equal to L, then there exists delta larger than 0 such that x is an element of E and provided that x is not x bar and the distance from x bar is less than delta, then the distance between the image of x and L is less than epsilon. Just the definition of limit. And now we go to the sequence. Now, moreover, since xn goes to x bar and xn belongs to the domain E subtracted the only point x, there exists an n bar, natural number, such that for every n larger than n bar, we have that once the distance between xn and x bar is less than delta, then f of xn minus L in absolute value is less than epsilon. So what we proved? We proved that eventually, after some n bar, the sequence f of xn is epsilon close to L. So by definition, of the limit of a sequence, we have final result f of xn is going to L. This is the first case, okay? This is the easy part, and you can complete by yourself this part, considering the case L equal to plus infinity, x bar in R. This is homework. Third case is the case L in R, x bar equal to plus infinity, and so on, homework. Fourth case, L equal to plus infinity, x bar equal to plus infinity, and so on. And then you can complete all cases. Complete all cases with the inclusion of plus and minus infinity. This is a good exercise. Don't be afraid to do boring exercise in this part of the course. Okay, it's your work to be a little bored now, because through boredom you learn a lot. It's like when going to the gym and making a lot of boring exercise, and your muscles become very powerful. Now the muscles of your brain have to become very powerful. Trust me. So however, I can give you also an alternative proof of this part. The alternative proof is with neighborhoods. We can do it in this first part with neighborhoods. So, and we don't have to distinguish between the various cases. So, very quickly, so since the limit for x going to x bar of f of x is equal to L, then let V be a neighborhood of L, then there exists a neighborhood U of x bar such that whenever, okay, let me use this definition, x is in U intersection E minus x bar, then f of x is in V. Okay? Moreover, since xn belongs to E minus x bar and xn converges or diverges in this case, it's just a limit, it can be infinite, to x bar, then there exists n bar such that whenever n is larger than n bar, xn belongs to U. Since it belongs to U, this belongs also to U intersection E minus x bar. Then f of xn belongs to V. So we proved that here, for every neighborhood V of UL, there exists an M bar such that after M bar, f of xn belongs to V. This is really wonderful. Okay, this is the proof for all previous cases, but it is more abstract, so you have to get acquainted with that. Okay, this was the easy part of the theorem. Don't get confused by the fact that I talked a lot to that. I gave you many comments, and also I gave you different ways to prove it. This was the easy part. Let us go to the difficult part. Okay, so the difficult part is the inverse proof. This is the difficult part. So for every xn, we assume that for every sequence xn with values in E minus x bar, but having a limit x bar, then the sequence of the images goes to L. We aim at proving that limit for x going to x bar of f of x is equal to L. You immediately see that it's difficult here because you start from sequences that are quite chaotic and are made of countable set, and you want to prove something that holds for a function that in general involves not countable sets. So it is not so easy. And the shortcut here consists in proceeding by contradiction. Okay? So we argue by contradictions as follows. We suppose that the statement limit for x going to x bar of f of x is equal to L is false. And we construct a sequence xn which lies in E minus x bar but converges to x bar such that f of xn does not go to L. This is the idea of a contradiction. If the thesis is false, if the conclusion of the theorem is false, then we can contradict the hypothesis, the initial assumption of this part of this implication of the theorem. Okay? So, difficult part here is due to logic. So we want to say that this statement here is false. So, therefore, we start by claiming that the limit for x going to x bar f of x is equal to L is false. Okay, here I have to distinguish cases. I'm not able to do this proof with neighborhoods. I only managed to do that with metric definition. So first case. The first case is x bar and L bounded, so real numbers. So we want to deny, we contradict that lim for x going to x bar f of x is equal to L. So we say the following, that it is false, here there is a not, it is not true that for every epsilon larger than 0 there exists a delta larger than 0 such that whenever x is in the domain of the function and the distance between x and minus x bar is less than delta, and always remember larger than 0 because x is not allowed to be equal to x bar, then the distance between f of x and L is less than epsilon. What happened here? Okay. I have to deny this, and remember that I want this not enter into the statement and go through the quantifiers. Here there is for all, it will become an exists. So this means that there exists epsilon, let me call it epsilon tilde. Tilde has not a special mathematical meaning, just to say that it is a specific epsilon. There exists a value epsilon tilde larger than 0, such that, here the not hits against this quantifier existing, so such that for every delta larger than 0, and what happens here it is written like an implication, but this means that it is hidden, but it means that for every x in E, such that this is true, then we have this conclusion. So this is a for every x in E, so there exists an x in E with distance from x bar less than delta and 0 and strictly greater than 0, then f of x minus L is larger or equal than epsilon. Okay? Epsilon tilde. So this is the logical contradiction of the definition of limit. But let us be careful and try to understand what does it say. It says that there exists a number, perhaps very little, I don't know, very small, but it is a number, such that in every neighborhood of x bar, even very, very small, in every neighborhood, there is a point whose image has a distance from L larger than the specific epsilon tilde discovered at the beginning. This is the message. In every neighborhood of x bar, even a very tiny neighborhood, there is a point x whose image is, let me say, epsilon tilde far, epsilon tilde distance from M. This happens when we deny the definition of limit. And now let us use the metric structure, the metric definition of the limit. And so consider now delta equal 1 over n for some n in n minus 0. This means that there exists a certain xn which is in E and which is not x bar, but whose distance from x bar is small, is less than 1 over n, such that the image of xn through f is distant from L at least epsilon tilde. Okay? And now we consider, so we let n run through all naturals. Then we obtain a sequence xn, which is in E minus x bar, such that xn, goes to x bar. Why? Indeed, we have x bar minus 1 over n less than xn, less than x bar plus 1 over n. Here you go through the two policemen, this goes to x bar, this goes to x bar. And so, by the double comparison theorem, xn goes to x bar. So this sequence converges to x bar because we are considering tinier and tinier neighborhoods, and xn is there. So xn converges to x bar, but f of xn does not converge to L. Because for every n, we have f of xn minus L is larger or equal epsilon bar, so the sequence of the images is never trapped in a stripe around L of width epsilon bar. So the theorem is proven. Then the hypothesis contradicted. And the theorem is proven. As a homework, all other cases, so with the infinities. With at least one of the two, x bar or L equal to plus or minus infinity. Okay, but here I think I'm not able to escape from the metric definition that makes it impossible to do it in just a proof. Here I am only able to distinguish all cases. If you find a way to do it with neighborhoods, very good. Send me your proof and we will check it together. So this is all for this chapter, and let us see what happens for theorems for limits.